I know some of you are, are following that parliament debate. Just mute yourself so that you don't hear any background noise. Okay, just to make sure that everything is in order. If you can hear my voice, then and see my screen, please type yes in the chat group. You see, I just had this feeling. I just have this feeling that one day, one of these days, when I ask you if you can hear my voice, type yes in the chat box, and then everybody is going to stay quiet. I just get that feeling. I know that one day is going to happen. All right, so there is some discussions going on in our chat group. Let me point out one of the most common mistake that the student will make when they want to get the characteristic equation or the overall transfer function. Even as I keep reminding you this, even I pointed out that this is a common mistake, some of you still going to do this. Some of you still going to do this. So this is the common mistake. See? Now, this is the most common mistake that the students make. Even as I scream out on top of my lungs, this is the mistake you're going to make. This is the mistake you're going to make. You're still making this mistake. This is not right. This is not right. You cannot do that. That is just freaking wrong. Even as I remind you, even as I draw this diagram, even as I cross it out using red marker, some of you still going to do that. Some of you. Not to mention the one that who never attend my class. No, that's not right. There. This is G divided by 1 plus GH. This is the overall transfer function. And the characteristic equation is the denominator. The denominator equal to 0, then you get the characteristic equation, not just this s plus 1, s plus 2 equals 0 equals 0. That's not characteristic equation. So don't do that mistake. No. You don't want to do that mistake. All right, so let us continue our discussion. It would be nice if we can determine whether the system is stable or not without having to compute the value, the numerical value of the roots. There is a test that you can conduct to know whether there exists a positive root or not. It is known as the Routh stability criterion. The Routh stability criterion is a method can determine the existence of positive pole. That's all we need to know, whether there exists positive pole or not. So the criteria is sufficient if we only wish to know whether the system is stable or not. But we will not know the exact behavior of the system. But never mind, it is a good test. All you have to do is obtain the characteristic equation and conduct the Routh table, construct the Routh table. So this is known as the Routh table. If the elements of the first column have the same sign, then we say that the system is stable. So how do you construct this Routh table? It's very small, whether you can see this or not. I have a bigger, probably mine is better. This is my notes. I wrote some notes. I post this on your e-learning so that those of you who do not attend my class will have some reference. I know. The attendance is not full, but never mind, forget about it. So we want to conduct this Routh stability criterion, whether to see whether the system is stable or not. First, you obtain this characteristic equation, 1 plus GH equals 0, and then you obtain the characteristic equation in terms of polynomial. See, it can be a polynomial of order n, fourth order or fifth order equals 0. Then you fill in the Routh table. Okay, so the first two rows of the Routh table, so this is the Routh table. The first two rows is filled in using the coefficient of the polynomial. So you take, if the characteristic equation is nth order, then you're going to have n number of rows, starting from s to the power of n, and going down to 0. The first two rows, the blue coefficient here, you fill in the first two rows using the coefficient of the polynomial, an, and then you jump an minus 2, you jump one coefficient, an minus 4, and the second row fill in with again the coefficient of the polynomial. You start with n minus 1, and then you jump 1, n minus 3, n minus 5, and so on and so on. So the first step is to fill in the first row with the coefficient of the polynomial, and then you fill up the rest of the elements in the table. So you want to know, you want to compute B1, B2, B3, B4, C1, C2, C3, and C4, and so on until you get to s to the power of 0. So what is the element B1, B2, C1, and C2? Okay, so here you need to realize the pattern. You need to realize the pattern. So B1 is -1. To compute B1, so you look two rows above you. So you take -1 divided by an minus 1 and multiply by the determinant of the two rows above you, above B1. So the determinant of an minus 1, an minus 2, an minus 3. Okay, so B2, again, to compute B2, the multiplier is the same. The multiplier for B1, B2, B3 is the same. It is always -1 divided by an minus 1. The multiplier of B is always -1 divided by an minus 1. The first column of the determinant is also the same for B1, B2, B3. The first column is always an minus 1, an minus 1. It doesn't change. You only change the second column. If you look here, the second column for B1 is an minus 2, an minus 3. The second column for B2 is, so this is B2. So you look one column to the right, which is an minus 4, an minus 5. So, and then that is how you compute B1 and B2 and B3. And similarly for C1 and C2, to compute C1 and C2, so you look two rows above. The multiplier is always the same. It's -1 over B1. Is the first element one row above you. The multiplier for C1 and C2 is the same. -1 divided by B1, -1 divided by B1. The first column of the determinant is also the same. So in this case, you look two rows above, an minus 1, B1, an minus 1, B1. is the same for C1 and C2, an minus 1 and b1. You only change the second column. The second column, you look one column to the right. So for C1, so you take an minus 3 and b2. And for C2, the second column of the determinant, you look one column to the right. So an minus 5, b3. So this is a pattern. Human always look for pattern. You look up to the night sky and suddenly see, okay, there's an Orion, there's Big Dipper, something like that. So if you can see the pattern here, then we are in business. You can now compute the rest of the coefficient, the rest of the elements in the table, and to test whether the system is stable or not, all you have to see is column 1, the first column, if the sign of the element of the first column are the same, and then you can say that the system is stable. The system is stable. Okay, so let's take a look at an example now. See? The system is stable when all elements in the first column of the Routh table have the same sign. For example, all positive or negative. Now let's take a look at an example. Okay. What the hell? Example 3.5. Determine the stability of the system with characteristic equation. This is a fourth order polynomial. And then here we want to construct the Routh table. Of course, I already constructed the Routh table for you. It's not that one. But you need to see how this Routh table is developed. Ah, okay, this is a step by step. What the hell is going on? Step 1, step 2. Forget about that. Okay, I'm going to my whiteboard. Let me double check whether it is the correct. S to the power 4, 5s cubed, 20, 40, and 50. Okay, since this is a fourth order polynomial, so you're going to start your Routh table at s to the power 4. So the first two rows, you fill in the first two rows using the coefficient of the polynomial. You start with 1, you jump to the next one, 20, and you jump to the next one, 50. So the first row, 1, 20, 50. 40s, yes. The second row, you start with the second coefficient, and you jump to the next one, 40, and there's no more there, so there's just 0. So now you need to compute B1, B2, C1, C2, D1, and D2. This is B1. So that's B1. To compute B1, you look 2 rows above. So the multiplier is -1 divided by 5. Is the first element on the on a previous row, and the determinant, you take the first column is just 1, 5, and then the second column you go one column to the left, 20 and 40, and then you can evaluate that. That will give you 12. So for B2, the multiplier is the same. The first column is the same, 1, 5. And you just change the second column, 5 and 0, 50 and 0. And then you can evaluate that. So that's going to be 50. Here, so B is equal to 12. B is equal to 50. That's it. So you continue. You can continue from there. You can now compute C1 and C2. C1, -1/12, 5, 12, 14, 230. 230/12. And then you do the same for D1, and you get 50. That's 0. Okay, so that's how you fill in the Routh table. This is and then to determine whether the system is stable or not, all you have to do is just look for elements in the first column. So in the first column, you have 1, 5, 12, 230/12, and 50. So all positive there. If they have the same sign, all positive, then you say that the system is stable. All elements in the first column are positive. Therefore, the system is stable. See, all the elements in the first column are positive, then you say that the system is stable. Do you have any question? Why we don't need C2? All right. If we make you feel any better, then you can compute C2. C2 equals 0. You can verify that C2 is equal to 0. See, because the second column here, there's no more elements there in the third column, so you just 0, 0. So finally, you get C2 is equal to 0. Any other question? That is how you develop the Routh table. Okay. Now, example 3.6. Determine the stability of the closed loop system shown below. So this is where you are going to make a mistake on your test. You say, okay, this is easy. I can do this. All you have to do is fill in the Routh table using the coefficient of the polynomial. Suddenly you fill in with just the denominator of that quotient. Then that's not right. So you need to obtain the characteristic equation. Then only then you can build your Routh table. Do I have that? Okay, so the step-by-step description of how to fill in the Routh table is described in my notes, in my handwritten notes. Okay. There, everything is there. You can go through that. And then you fill in the element and look for the first column. Okay, so therefore the system is stable. So these are the elements in the first column. All right, so the first time, of course, we need to do into detail. After this, you just fill in the Routh table very quickly. Okay, now this is an example 3.6. A typical example, a typical question in your exam. In the process of you too eager to construct the Routh table, you just take s to the power s cubed plus s squared plus 2s equals 0, and then you go on from there. No, don't do that mistake. First, obtain the characteristic equation, which is 1 plus gh equals 0, and then construct your Routh table. Okay? Fill in the coefficient from the characteristic equation. So this is a third order polynomial. So you're going to start at s to the power 3. The first row, you fill in with the coefficient 1 and 2. And the second row, you start at the second coefficient, and then you jump 1, and you get, so 124. 1, 2, and 124. And then you can now compute the rest of the elements in the table. And then to see whether the system is stable or not, you look in the first column. You start with 1, 1, negative 22, negative 24, 1, positive 1, negative 22, positive 24. See, you have a sign change there. If see all the elements in the first column do not possess the same sign, then the system is unstable. The number of sign changes will tell you the number of positive roots. Here, positive, positive, negative, there's one sign change, and negative to positive, there's two sign changes. Therefore, this indicates that you're going to have two positive roots. There's a question in the chat box. Question will ask for Routh method. Is it, or is there any criteria? Most of the time, the question will not ask you which method that you should use. The question will ask, determine the stability of the system. That's it. And then it's up to you whether you want to find the exact root or the Routh table, unless the question specifically say that use the Routh criterion to determine whether the system is stable or not, then you have to develop the Routh table. As some of you who possess some calculator that can compute the Rouths, you don't want to learn how to construct the Routh table. I got that. I understand that. But sometimes the question will specify for you to construct the Routh table. The last variable I get 0, is it considered stable? If you have 0, then the system is marginally stable. See, if you have positive, 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 and one element is 0, then that indicates that the system is marginally stable. One of the roots lie exactly on the imaginary axis if you have 0 in the first column. I hope I answered that question. So here you have two sign changes. So that, how to spell what? Unstable. How to spell it? Spell what? If all 0, if all 0, then you don't have a system. You have nothing. Everything is 0. It's like, no, you're not going to get all 0. All 0 meaning that you don't have a characteristic equation. All 0 meaning that 0s cubed plus 0s squared plus 0s plus 0 equals 0, and you have what we call a trivial case. We are not interested in a trivial case. See, 0s cubed plus 0s squared plus 0s plus 0 equals 0. What the hell is that? It's so trivial. Is that there is a trivial system? It means that you don't have a system to control. Where was I? Okay, here I was talking about the number of sign changes. You have two sign changes, meaning that you're going to have two positive roots. So for this equation, so I have determined the roots. So the roots are -3, and there's two positive root here. It is a complex number. It is a complex root, but the real part here is positive. So the number of sign changes in the first column indicate the number of positive roots. What else do we have? See? It is not difficult to develop the Routh table, but just when you think that you have everything, see, life will always 3.7. This is 3.6. We are done. We are done with 3.6, right? This is 3.6. Okay, 3.7. Okay, 3.7. is done. So it looks like it is not that difficult to develop the Routh table. But just when you think, just when you think that you know how to answer the question, most of the time we are not that lucky. There's always something lurking behind us that sometimes determine our luck, whether we can do it or not. See what happened if one, okay, what happened if one of the element in the first column is 0? Then you cannot proceed because the multiplier now become -1 divided by 0. Or in case this example 3.7 here. See, when you fill in the first two rows and then you compute the first element of the third row, you get 0 there. See, you cannot proceed to the rest of the rows because the next multiplier will be -1 divided by 0. You cannot proceed. So if there exists a 0 in the first element, for you to proceed, and you need to replace that with a positive small number. You can see here that B1 is going to be 0. So the next row you cannot compute because the multiplier is -1 over 0. And then you replace B1 with some small positive number, then you can fill the rest of the table. So now B1 is 0, but if you put 0 there, you cannot proceed with the computation of the rest of the element. So we replace 0 with a small positive element epsilon so that you can now proceed computing the rest of the element. So so the multiplier of C1 is no longer 1 over 0, it is -1 over epsilon, and then you can now compute the rest of the element. And then again, since this is a negative, there's one negative element in the first column, then the system is unstable. Okay, the system is unstable. All right, so we are at the end of this Routh table discussion. Let's take a look at the last example here. So this last example, instead of epsilon, can I use other? Normally, it is a standard symbol. Epsilon is a small positive number. Epsilon. You can use other symbol if you want, no problem. But mathematicians normally use epsilon to indicate a small positive number. All right. So now here, determine the range of k to ensure the closed loop system is stable. So we want to know the value, the range of k that you can have so that the system is stable. You cannot, when design a controller, you cannot have a very large value of proportional controller. So in this case, we want to know the maximum value of k that still make the system stable. So we can use the Routh table to determine the value of k. Let's go to my notes. Okay, so you obtain the characteristic equation. Do not just get the denominator of g equals 0. That is incorrect. See, the first step is always to obtain the characteristic equation and then construct your Routh table. Third order, and then you have this 130 in the first row, 13k in the second row, and then you proceed to compute the rest of the element. For a stable system, you want all the elements on the first column to be positive. So k must be greater than 0, and k cannot be greater than 390. If k is 390, then you're going to get, if k is greater than 390, then you're going to get a negative value for your B1. So for stability, you want your k to be greater than 0 and less than 390, or you can put that in an equality. So this is for stability. K must be between 0 and 390. Do you have any question? All right, so that's the end of today. So that's the end of today. We'll discuss new topic next time. If you don't have any question, then I'm going to end our class here. Do you want to take a break tomorrow and celebrate Deepavali or something? See, we have not. What do you mean by the same sign? All positive is considered the same sign. See, all negative is also considered the same sign. See, the characteristic equation, you can multiply everything by negative, then you have all negative. As long, see, the characteristic equation is not, you can multiply everything by -1 and you get negative s to the power of 3, negative 13, negative 30, negative k is equal 0. And then all element in the first column is going to be negative. As long as they have the same sign, meaning all negative or all positive, then the system is going to be stable. That's what we mean. That's what I mean by same sign. Negative sign or positive sign. Do you have any other question? All right, so I'm going to stop there today. I'll see you again tomorrow. Okay, so see you again tomorrow.